Right, sorry about that. We have been talking about this make-believe temperature regulation system in a room. We had gathered all of the physical things we had in a Gilligan's Island style of design. I listed out a couple of vague qualitative requirements, and then I brainstormed a couple of specifications quantitative to those qualitative requirements. The second step was to draw this functional block diagram, which was all basically had the major components that we had listed in that physical part of step one, but not a whole lot of detail in how each of these systems works. Basically making sure you've got all the components in the right place. Something to check when you're drawing your block diagrams, whether they be Laplace or functional or whatever, is that when you go to add signals, add or subtract, these two signals have to be the same units. All right, so that's a double check for you. Whatever units this has to match, or else this addition won't make sense. Same here. So on Monday, we said that this was the heat dumped by the heater into the room, which means this would have to be the heat lost out of the room. So these would both be measured in, say, joules, which means that their difference is also measured in joules. Okay? That is, this is not Fahrenheit. This is not, like, they have to match, whatever they are. This might be Fahrenheit. This might be Fahrenheit. But however we interface and however we sense, those have to then be the same units. Yeah? And I think we'll see that these are not volts, but these are actually angles in our manual bimetal thermostat example. So this is going to be rads. And rads. All right, so let's get, any questions on this? Let's start talking about schematic. It says a schematic, but when you've got a system with lots of moving parts, so to speak, it's often easier to draw separate schematics for every subsystem. Okay, that's the tactic I'll adopt as well. So for the user interface, there's not much to do here. Remember, in the thermostat from Monday, it was just a lever. So I'm just pictorially representing the user interface. The main advantage of doing this is I start to think about what are my variables, what are my signals, what are the things, and what are my reference points. So maybe I want to measure this angle as theta set. Or maybe I want to measure it from here. I don't know, it actually doesn't matter, but drawing this picture gets you to think about asking that question, which is the first step. Right. I said that these would both be measured in terms of radians, so we have our first signal. If the user changes this lever angle, they're going to change theta set, okay? And that is how we, as systems engineers, are going to interface with the user. Does that make sense? Very simple. And I'm calling it a schematic, which is a fancy word for something that's very simple, so I don't want you to get thrown off here. All right, what's next? Let's dive into the bimetal schematic. So I'm going to try and simplify things here. It was, in the thermostat I brought in, it was wrapped around 3 or 4 times. I'm going to abstract that to be a single wrap. So let's see, it looks something like this. Where I actually want to exaggerate this a little bit. Cool. So I would like to eventually connect all of the drawings, all of the schematics I'm going to put up here. And the way that I connect this guy to this guy is that this orientation, this angle, is also going to be theta set. If you were paying attention to the close-up yesterday or Monday, when I moved the user interface lever, the thing that pivoted was the center of the coil. And so what else do we have here? Here we have the same reference line, vertical, corresponding to another angle, maybe theta O. Now that I've drawn this picture, I might have to go up and look about some of the heat transfer characteristics of these metals, but I'm probably going to need something like a radius. And I'm also probably going to need something like a total length. Now you can maybe see why it was simpler to draw it as a single coil rather than as multiple coils, because then you have to deal with the radius that was increasing constantly. But we're not MEs here. We're going to treat this as a single thing. It'll be hard enough. All right. Does that adequately represent our controller? I think it's good enough for now, but yeah, go ahead.
Okay, so in the bimetal schematic, is that's supposed to be two different metal strips wrapped around each other? I'm just a little confused on the picture.
Let's zoom in here. I've got, what is it? It's alpha, I think it's low expansion. We'll call it alpha 1 and alpha 2 for now. Coefficients of thermal expansion. And these are bonded together rigidly along this interface. Okay. Any other questions? So now, let's talk about heat transfer, which is again outside your realm of expertise, I assume, but let me walk you through it. So, okay, also, the reason I'm not doing a purely electrical control system is that it's actually really, really hard to find linear electrical control systems. They almost all have transistors and diodes and nonlinear things in them. And while I know that most of you have taken 306, 307, etc., they're not technically prereqs for this class, which is why I'm a little handicapped in my ability to give you something that you're more used to. All right. Is that a good enough excuse? Well, it's good enough for me. So okay, so this bimetal schematic roughly corresponds to, well, actually this part of the functional block diagram, right? Temperature sensor, as well as the summing and differencing, as well as the amplification, is all being done by the coil. So let's talk about how does the heater and the room and the heat loss interplay. Have any of you taken heat transfer or anything about thermodynamics? Okay, you're gonna love this. Okay, so I was a mechanical engineering undergrad. My BS and MS are both in mechanical engineering. So that's kind of where I'm coming from. That was also a long time ago, but that's not important. When we, as mechanical engineers, learned about heat transfer, part of that class was drawing what they called thermal circuits. And so, to mechanical engineers, This is terrifying, okay? But this is analogous to the heat transfer problem that we're about to treat, okay? So it's heat transfer, but as a circuit. So I'm bringing it all the way back around for y'all, okay? Anyway, so heat flows, okay? It is a flowing type quantity, a lot like current flows. I'm going to represent the heat provided by our heater as a current source. Okay? The current is heat. Now, this is a very important distinction that takes many weeks in mechanical engineering classes to get everyone straight on. Heat is different than temperature. If heat is like current, can you help me out? What is temperature like in a EE?
Voltage.
There we go. The voltage of the room corresponds to the temperature of the room. The capacitor represents the room's ability to store heat, much like a capacitor actually represents the ability to store charge. All right? So you fill the room with different stuff, like a huge tank of water or 40 smaller tanks of water, and its capacitance will change, but nevertheless, its ability to retain heat is represented. What do you think this resistor should represent? Is it? So, and okay, this might need more than you know, but a resistor dissipates voltage or drops voltage, or rather passes through heat. Sorry, I'm mixing up my own analogies. The resistor passes current based on the difference in voltage across it. That's kind of like what a wall does. It transmits heat based on the difference in temperature across it. Okay, so this is more like the natural insulation of the wall. And the reason I'm not representing the window being opened here is because the heat loss through the window doesn't necessarily follow an Ohm's law characteristic, does it? It's going to be kind of arbitrary, which suggests it should get its own current source.
Could the resistor also be represented as the room in the schematic?
One more time?
Could the resistor also be represented as the room in the functional schematic?
I think that if you were going to make a mapping from this picture to that picture, these would both be part of the room, in my opinion. Yeah. So, because it's an independent current source, the amount of current it conducts is not dependent on the heat in the room or the heat outside, and we can vary this as an independent source. Small window opening, small current, huge window with a fan, large current. All right? Look at that, heat transfer, not so bad. All right, I think we've got everything. And I want to impress upon you the difference between this picture and these pictures. These have much more detail than here, but it would have been hard to draw these three individually if we hadn't set up this big picture first, in my opinion.
Where are we taking the output of the thermal schematic? That's going back into the temperature sensor. Is that just
One more time?
where are we taking the output? Because the output of the thermal schematic is view room.
Yep. Yep. It's not your job.
And so then then the bimetal, how that relates to the thermal, is it controlled by here, or what's the link there?
Yeah, good. So now we need to take these and do some analysis on them. In particular, how does temperature or heat affect this? I'll give you the big picture first, or I'll Tarantino it. I'll go to the end and we'll come back to this. This is going to toggle heater on or heater off. Okay, so it's not a strictly linear system because it's a binary state. But the output of this is going to be an on-off signal. The input are going to be angles. And how do we get an angle out of a temperature? Well, that's the physics of this bimetal strip. Okay, so let's talk a little bit about coefficients of thermal expansion. So, in general, your percent change in length, and again, if you tune out for the next 5 minutes, it's perfectly okay. This is not EE stuff. The change in total length of this coil relative to its kind of natural length is given by the alpha in the nickel minus the alpha in the brass, where nickel is a lower alpha than the brass. That just has to do with the physics.
Is the inner one the lower one or the higher one?
Sorry?
Is the inner metal the higher? Is alpha 1 the lower one or higher
So
one?
let's settle this once and for all. When the temperature goes up, I want the heater to turn off. So the way that I've drawn this, as the temperature goes up, I want this to contract. Let's flip that around. As the temperature goes down, I want this to expand. So as this goes down, I want this side to get bigger. So I need this to be negative, which it will be. And that physically happens. If this goes down, that means, oh, it's easy for me to think about when the heat goes up. So when the heat expands, I need the inside to get bigger than the outside. This will be brass, this will be nickel. I could have just flipped a coin and no one would have checked me on it. We can talk about it later if you need me to walk you through that without me mumbling at the board. But the idea is, if I want this coil to expand, then I need the inner metal to get bigger faster than the outer metal.
I don't know if this would really apply to what we're going to be focusing on, but if you just switched like what was the off and on state at the actual switch, then would it matter what the metals are?
In fact, if anyone calls me on this and it's wrong, I'll just say, okay, we're going to switch the switch locations.
Okay.
Yeah. So keep prepared for that.
And so did you just arbitrarily pick which is on and which is off for this case?
No, I wish I'd brought the thermostat because I could have showed you that when the switch goes here, the circuit is opened, and when the switch goes here, the circuit is closed.
So it's expanding and contracting is on or off, which one is it again?
So this one is going to give us heater off, and this one is going to give us heater on.
So is theta set the one that moved, or is theta O?
They both move. That's the point. That's this summing junction. We can change theta set by moving the lever. The temperature in the room then does its thing to expand or contract the coil, which then adds to or subtracts from theta O.
So once we set the temperature, let's say we don't touch it anymore, So data set stays at that position that's
Uh-huh.
there, and then if it gets colder, then we want the heater on, so then it, expands, so then data only moves that way.
Yeah,
Okay.
yeah, good. And the addition is subtle here, yeah? Well, the subtraction is even more subtle, because the first time I did this, I had these in the opposite direction, and it was an addition, but we want it to be a subtraction. The addition happens because this angle is this angle plus the angle given by the coil. That's a very subtle point here. There's no summing amplifier, there's no business like that. The addition is simply one angle adding to, you know, an arc starting at a different angle. All right, what do we got here? We got some, if I move the L over and my change in length, if I think about an arc, this change in length corresponds to a certain change in theta depending on the radius. So there we go. Delta theta O is going to be delta L divided by the radius of the coil, which is itself negative delta alpha times T over R times L. Yeah. And this is temperature of the room. And you should probably note that this I'm defining as negative delta alpha, primarily to get that negative sign. All right. We good on this? Any questions? So let's talk about this circuit. What I would like is a transfer function, because in my Laplace, I'm looking into the future. My step 4 is called a Laplace block diagram, and inside of that Laplace block diagram, we're going to be a bunch of transfer functions. This is a transfer function from room temperature to angle. So it's just, there's no S's here because it's an amplifier. Here, we're going to have some dynamics because we've got the capacitor. But there's 2 inputs to this circuit. Yeah, there's 2 independent sources. So I think what I'd like to do is define I net as the difference between the heat given to us by the heater and lost out the window. Okay, so then KCL says the current into the top node has to equal the currents coming out through the cap in the resistor. So that will be capacitance of the room times the time derivative of the room's temperature / voltage plus the current or heat lost through the wall. Okay, all right. I never doubted you for a second. All right, in Laplace land, what do we get here? We get I net in terms of S equals C room times S times V room, plus V room over R wall. This V room is a function of S. So I think we can get a transfer function. Ooh, is it obvious what's the input and what's the output? That was a terrible way to ask that question. What's the input, what's the output? What goes over what here? Good. The voltage is the output, the current is the input. So at the end of the day, I want output over input. What do we get here? We get R of the wall on top, S C room, R wall, plus 1. Cool.
I'm still a little confused as to the link between the bimetal and the kernel. So, did we not? It seemed to me like you would want to model with a switch that either shorts out, or not shorts out, opens or closes to enable the ID, or are we just modeling it as a symbol instead?
So you're right, we have not explained where this signal comes from. I vaguely waved my hands and said it's going to have something to do with theta O, but I'd like to formalize that now. All right, so our Laplace block diagram is actually going to have the same input and the same output as our functional block diagram. How should we convert the set temp to theta set? What's a good representation of that? I left that blank here, right? That would be the math that goes right here. I would really like it to be linear. I would really like it to be a scaling factor. The way that you could check this would be if this is, I think, 50 degrees and this was 80 degrees, just make sure that if these are evenly spaced, these angles are evenly spaced. And as long as you make these demarcations properly, that'll be true. So they're going to use some scaling factor that changes the temperature in Fahrenheit to an angle. All right, so in order to get theta O, we are going to subtract this stuff. So delta alpha times length over radius. If I scale T room by that quantity, I get a change in theta O. That change in theta O, when added to theta set, will give me the true theta O. Here is where I have to put quotation marks around Laplace, because we're coming up to a non-linear element, that is, a binary switch. Okay?
What is the KU block?
Whenever I come across a constant in this class, I'm probably going to call it K. So this is just some scaling factor. Yeah. All right. So I will give you a fair warning here. This is not strictly speaking of a Laplace block. We're going to model it as a take the sign of the input. If the sign is positive, then we'll set the heater to its max. If the sign is negative, we'll set the heater to be 0. This is the on-off gas furnace that you'll find in old homes. Only one of these two will be on at any one time, so I'm going to multiplex them together. This output will only be this one or that one. It will never be both. So this multiplex is kind of superfluous, but I needed a way to mix these two signals back into one. All right, and so the output of this summing junction, well, that looks a hell of a lot like this. Take the heater, subtract the loss, and I get the net current. And I have left myself not enough room to write that transfer function. Probably the last thing to do is recognize that there is a limit to how closely we can identify currents with heats and voltages with temperatures, and that comes down to their units, right? If we solve this in terms of our typical EE units, we get a voltage in volts. And I need to convert that to a temperature. Go ahead.
Can you explain the block on the bottom you drew on the Laplace one?
Sure thing. Oops. So, from our bimetal schematic, and also from the heat transfer physics that I kind of vomited at you, we got a relationship between the temperature in the room and the net change of this coil's total angle. And so one way to write this would be as a scaling factor times this signal, T room. And that's exactly what I've done here. So this is a transfer function, but it's actually just a scaling factor. Because I'm taking the temperature in the room, I'm scaling it by these parameters, and I'm getting delta theta O, which I'm then subtracting because I omitted this negative sign from the box, and I moved it up here.
Okay. So you're saying that you're just saying that data set and then just the heat in general is then contributing to the theta O that we have.
Exactly. When I breathed on this, the coil changed a certain amount, and that would be the delta theta O.
And then so also theta set is changing theta O as well at the same time.
Well, I could have been moving the lever and breathing at the same time, but in the demo on one day I wasn't. But in principle, yes, you could do that. So you see that there's two contributors to this final angle. There's the angle that you quote unquote start at, and then there's the angle contributed or subtracted from by the expansion and contraction of the coil. Those are these two signals. Question?
I was just gonna ask what that says next to the second
Units. It's a unit conversion. If you're clever, this can be 1 and you can ignore it. So, okay, those are all good questions. And thank you for asking me. Now that we have a mathematical Laplace model of the system, now we can go and actually figure out what each of these parameters does. Right? We haven't designed anything yet. Principally, what I would be interested in as a control engineer would be what are the effects of these three things? But straight away, I can see that delta alpha and L both contribute in the same way, which is the inverse of what the radius does. So if I'm looking to design that coil, I could either make it longer or with a bigger radius. Sorry, or a smaller radius, and that would have the same effect. Sizing the heater changes nothing except for the size of this signal, which is a little surprising if you think about it. If you have a 500 watt heater versus a 5,000 watt heater, nothing else changes except for the magnitude of this step. Yeah? All right. I guess I exceeded the slide, but you guys probably figured that out. Any other questions? This is about where I'm going to leave it because we haven't covered how to reduce block diagrams yet. So I think this was not nothing. We are going to be doing a lot of work around DC motors, both in lecture and in lab. One of the principal components of your term project is going to be a DC motor. So I wanted to introduce them to you now. I think you did them in 255, 295? I know. Don't give me that look. I've seen that look a lot. I will try and cover everything you would need to know for this class in this class. It should be self-contained. It also should be congruent if you remember anything from 255, but I'm not counting on it. All right, so in general, we've got a stator and a rotor in a motor. In the stator, we've got an armature circuit. We can model that as an armature resistance, an armature inductance, and a back EMF. And if we change the voltage on the armature, we can change the current flowing through this circuit. Let's call that VA of T. Let's call this the current to the armature, function of T. And if you remember your 255, the back EMF is generally proportional to the speed of the motor. Motor spins faster, the back EMF increases, which means the voltage you applied here has less and less effect. Okay. So let's call this KB times omega motor. The rotor side has a torque applied by the motor. It's got also a torque related to the friction, either air friction or friction within the motor stator or rotor stator interface. And then the rotor and anything you connect to the rotor has a moment of inertia. And we will take positive speed as this way. Omega motor, sorry. How does this schematic interface with this schematic? generally speaking, that's a complex relationship, but we're going to treat it as linear. The torque generated by the motor is going to be linearly proportional to the current through the armature. We'll call it the motor torque constant times the armature current. And that's the last time I'll reference 255, I promise. This is all you need to know. Do you see how these are both independent schematics and they were connected by another physical relationship? I drew the circuit diagram, I drew the free body diagram. These are two schematics that represent different subparts of a DC motor system. Let's take these schematics and convert them into a Laplace block diagram. That generally involves converting into the Laplace domain and rearranging for transfer functions. So what do we know here? We know, well, in Laplace land, this is a resistance. This is SLA. The Laplace impedance of an inductor is S times L. And so the current in the Laplace domain is the change in voltage across the components divided by the impedance, which is R plus SL. The back EMF can be replaced by a scaling factor times capital omega. I'm sorry the capital omega doesn't look like lowercase omega. It's not my fault. But I'm trying to respect that time domain things are lowercase, Laplace domain things are uppercase. It kind of backfires there. All right, so if our armature voltage is an input signal, I've got a minus sign here, which is a surefire clue that I want to put a minus sign here. This signal, the yellow one, is KB times the motor speed. How do we get the motor speed? Don't know yet. I'm going to leave that dangling. And that's okay. I want you to be okay with that. Part and parcel of the fun of all these Laplace block diagrams is you get to jigsaw them together. Personally, I can't stand jigsaws, but I actually do like this, so I don't know. So this summing junction gives us the numerator here. If I then divide by this, or multiply by the inverse, 1 over RA plus SLA, the output of this is the armature current. The armature current, scaled by the motor torque constant, gives me the motor torque. Now we can do F equals MA on this rotating shaft. Or T equals JL, yeah. Rotating Newton's second law. You all know this one. You also know this one. It's just, everything is rotating now. there's a sigma here, there's a sigma there. Alpha is theta double prime, just like A was X double prime. So what are our torques here? There's the motor torque in the positive omega direction. There's the friction torque in the opposite. And that's it. That's all the torques that we're modeling here. Moment of inertia takes the place of mass when you're talking about rotational problems. And theta double prime is the same as omega single prime. Oh look, a diffie Q. I mean, it is a diffie Q, but I wanna sub out the tau f. I wanna model the friction as being proportional to speed. Go ahead.
Sorry, where did omega m single prime come from?
Angular acceleration is the derivative of angular speed, which is the derivative of angular position.
Okay.
Yeah, it's just like linear stuff, where it goes acceleration, velocity, position, but you throw angular in front of all of them. All right, so here's our diffie Q. If I move this guy over, I get tau m in the time domain is equal to kf omega m in the time domain plus j omega m prime in the time domain, which is in Laplace land. Tau m of s equals kf plus js times omega m of s. I'm kind of heavily relying on you remembering that time derivatives involve multiplying by s in Laplace land. All right, I'll be done in just a moment. We get 1 over kf plus s times j. The output of this is omega m, which is what I need to complete my jigsaw. Sorry for going over time, but we'll pick up from here on Friday. I'll stick around for questions.